Alright, tonight's video is a continuation of what we looked at in our last video. So now we're going to look at the life cycle of big stars. So by big stars, we are talking stars bigger than our sun, alright, and generally at least 4 times bigger. Alright, and so the first thing that doesn't actually have a slide on this, but we're going to talk about it quickly, is the early life. And I'll write this out just because there are no notes for it. And the early life of a big star is much the same. It starts as a nebula, and gravity pulls it into a protostar, and then finally the gravity continues to pull it together and a main sequence star forms. Right? Remember, bigger stars tend to live less long, so bigger stars have shorter lives. So kind of keep that in mind when we're looking at this. And by shorter, again, it's all relative. It might be 1 billion years instead of 10 billion like our sun, but it is shorter than a smaller star would be. So let's jump right into then how these stars die. And so massive stars, at least 4 times bigger than our sun again, still are going to puff up into red giants, but they get so big that we actually give them their own classification. We call them supergiants. Alright, so we are going to have supergiants, and now you guys are going to go back to it. And so to give you just some size comparison here, the sun isn't even visible in this picture. It would be literally 1 pixel on your screen. Here are some examples of red giants: Arcturus, Aldebaran. These are stars that are dying. Right? They may have been the size of the sun and have now puffed up to a red giant. Then you have stars like Betelgeuse and Antares that are red supergiants. All right, so it's the same process, right? They're running out of fuel, they're dying, and they swell up. But since they started so much bigger, they swell up even more massively. So if you remember the video we watched, that largest known star, that's a red supergiant. All right, sometimes they're so big they're called hypergiants. Same thing. And then for a big star, instead of just collapsing down into a white dwarf, when it really runs out of fuel and collapses back in, it becomes unstable and explodes into what's called a supernova. Alright, so in a supernova, alright, these are the largest, most powerful explosions in the universe. Alright, so this star is literally blowing itself apart. Alright, as it collapses in, all that pressure creates instability, and instead of just collapsing down into a white dwarf, that instability causes it to explode outwards, and these are some of the brightest things you can see in the sky. Sometimes they're so bright that even though they are billions and billions of miles away, they can be seen during the daytime. And what's cool about them is in these supernovas, they have so much energy that they create new kinds of material. Right? So heavier atoms such as like iron and lead and aluminum, all right, are made in these supernova explosions. Right? This is an example of an old supernova, so you can see clearly. This is obviously a very zoomed in picture from a telescope, but here's where the star used to be, and then this ring of gas and dust is expanding outwards away from it, creating a new nebula that can later form a new star. Right? So we're kind of recycling everything back around again. Alright, so the leftover stuff that didn't explode out, alright, the super dense core is going to collapse in on itself and form 2 options. So the first option is a neutron star. Alright, so this would be, again, like the mass of the sun. So a lot of that material in the supernova blew out into space, but some is still there, and gravity causes it to collapse in super dense. Alright, so you might have something the mass of the sun in an area of space the size of Atlanta. Alright, so we are talking super tiny. Alright, a teaspoon, if you were to take a spoonful of neutron star, it would weigh over 10,000 tons. That gives you an idea of how densely packed that stuff is, right? Density is mass per unit space. So this is crazy dense. And if it's an even bigger star, so this is our second option for stage 6, for a massive star, we are talking over 10 to 20 times the size of the sun, it can form a black hole. And so what happens here this huge mass is left behind, and it collapses in on itself, and there's so much mass crushing into such a tiny space that its gravity becomes so strong that it prevents even light from leaving it. So this is an area of infinite density. All right, and I'm going to add that in over here. So we had our supernova, so we had a neutron star, and then we have a black hole. Alright, so you should have taken your own notes as you went along. And I just want to add a black hole as an area of infinite density. Remember, density is mass over volume. This is an infinitely large mass in an infinitely small space, which is crazy to think about. But it does have a mass, and you can orbit a black hole safely just like we orbit the sun. So I guess earlier I misspoke. It's not an infinitely large mass. It is a fixed mass, but it is in an infinitely small space. So that that's where we get that infinite density. All right, but you can safely, safely orbit a black hole just like a star. Right, and it turns out our star, our sun, is orbiting a black hole at the center of our galaxy. We'll talk about that a little bit more later this week. But just because a black hole exists is not a giant vacuum cleaner of doom. It does not suck up everything in its path. All right, things that get too close will get pulled in, just like things that get too close to the sun will get pulled into the sun. But you can safely orbit a black star, or a black hole rather, just like you orbit any other star. All right. So I'm sure you all have some questions. All right, we'll talk more about black holes in class tomorrow. Please put 3 questions at the bottom, and I will see you guys in class tomorrow.